So welcome everyone to this week's string seminar. We have Daniel Harlow from MIT. He's going to talk about the black hole interior from non-isometric codes protected by complexity. Over to you, Daniel.
Hi, so thanks so much for the invitation. It's great to be able to talk to you all finally. I'm sorry that we didn't manage to make it work last semester, but here I am now. And of course, one of these days, months, years, it would be fun for me to actually go and see you all in person. I'm going to talk about work with Chris Akers, Netta Engelhardt, Jeff Penington, and Shreya Vardhan about the black hole interior from non-isometric codes protected by complexity. And unfortunately, the paper is kind of a monster, so I'll try to kind of convey the essence of it, but there's a lot of details that I will suppress unless you ask me about them. So feel free to interrupt me whenever you want, complain, ask questions, etc. That's part of the fun as far as I'm concerned. In quantum gravity, we've thought for a long time, I guess most of us at least, that space-time should be some sort of emergent notion, which is only valid in certain situations and in some approximation. So this is not a universal belief, right? People, for example, loop quantum gravity in some sense denies this idea, but I guess probably most of us would agree with this. In ADS CFT, this kind of vague idea of emergent space-time is described mathematically using this language of quantum error correction. You can decide whether you want to call the language quantum error correction, but either way, the mathematics is the mathematics of quantum error correction. So a simple example of that is if you look at what is usually called a code subspace of states, which a simple one is just you consider all the states in the bulk that don't have any black holes. Okay, so you might say, well, that's a boring subspace. Okay, fair enough, but let's try to understand that one first. And then the idea is that if you take the Hilbert space of these low energy bulk states that don't have any black holes in them, then there is some linear map that maps that isometrically, or at least approximately isometrically, into the microscopic Hilbert space of the boundary degrees of freedom. So we have this bulk degrees of freedom, the dots filling the bulk space-time, but then that's not really fundamental. It's really these degrees of freedom that are fundamental, and there's some linear map that pushes these into a subspace of those, right? And it's only going to be a subspace because we're not including the states with black holes, at least on this slide. So that was the picture that we argued for in 2014. And there are various nice aspects of the map that have to do with it sort of being a good quantum error correcting code. Those are not so important for the talk today. Now, just to make sure everyone's on the same page, let me just remind you that when I say approximately isometric, so an isometry is a linear map from Hilbert space A to Hilbert space B, which preserves the inner product, which is the same as saying that V dagger V equals the identity. Now you might say this looks like a unitary. It's a unitary if A and B have the same dimensionality. But for an isometry, they don't have to. But on the other hand, in order for an isometry to exist, you at least need the dimensionality of B to not be smaller than the dimensionality of A. Okay. Yeah, if B were smaller, then there would be no such linear map. Now, okay, come on. Black holes are what make quantum gravity fun, so let's talk about black holes. So you can extend this idea to states that have black holes, but at least if you want to do it in the obvious way, when you do that, you have to only allow the encoding map to act on the exterior degrees of freedom. So now we have the dots that are outside the black hole, and the black hole is we view it as some object that, say, is in some fixed state. And we don't try to understand the space-time inside the black hole. We can, if we like, we can include microstate degrees of freedom for this black hole in addition to these exterior modes, and we can map that here. But we just say that there's some set of microstates whose dimension is e to the a over 4g, and we don't try to interpret those as interior geometry of the black hole. So if we do that, then you can have an isometric map as before, sort of from black hole microstates together with exterior degrees of freedom into the fundamental boundary description. Okay, so that's also been understood, roughly 5-ish, 10-ish years, I don't know. Unfortunately, you can say, okay, fine, but what about the black hole interior? Isn't that what we, are most interested in? Or it's certainly something we are very interested in. And it's been understood for a while, in various ways by various people, including Subrat, that you can't reconstruct the black hole interior in this way, where you just have this nice isometric map pushing you into the fundamental degrees of freedom. And I'll say in the next slide, I'll give one version of why you can't have that. So today I'm going to present a proposal for how the reconstruction can work, which then I'm going to be able to apply to the black hole information problem. And that's based on this paper that came out, I don't know, maybe a month ago now. Okay, so let's proceed by contradiction. So let's try to construct a holographic encoding map for the black hole interior, and then see how we get into trouble. So here's the basic picture. So I'll say what I'll try to do is think about what's the so-called nice slice in effective field theory. So this is a Cauchy slice that starts out outside the black hole. So for here I'll be considering flat space black holes mostly in this talk. We can also think about ADS black holes, but I'll mostly leave that for the questions. So you have some Cauchy slice that starts out, near spatial infinity, comes in behind the black hole, and has inside the black hole, there are left movers, which I'll call little l, and right movers, which I'll call little r. And so for this talk, I'm going to ignore the interactions between left and right movers. Apologize. I think they could be included, but it would just make everything messier. So this is the bulk description, or we'll call it the effective description. It's the bulk effective field theory picture of what's going on. And then the idea is that we would like to have a holographic map that takes these interior degrees of freedom and maps them into the microscopic black hole degrees of freedom. So this HB is the Hilbert space whose dimensionality is e to the a over 4g. So it takes these interior modes. There's a linear map that pushes them into the microstate degrees of freedom. And then if I have some, radiation or reservoir or some exterior system that the black hole is coupled to, which in this picture is just sort of the rest of flat space, then I'm going to want this map to just act as the identity on the reservoir, because the idea is that, holography, the sort of weirdness has to do with how the black hole interior is mapped into the microstates. This is a bit of an approximation, right? I mean, really flat space itself should be holographic, and so this R should really be mapped in some non-trivial way into the BFSS model or something like that. I don't think that that's a crucial issue for the talk that I'm giving, but just to make sure that it's not, we're going to play this game that was introduced a few years ago, where we just have a non-gravitational reservoir system R, some spin chain or something, and then we just couple it to some, if you like, ADS big, CFT, which is dual to, to a big ADS black hole, this B here. And so this encoding map maps you from this nice slice in the gravity region, this Cauchy slice in the radiation region, and then you're pushed by a linear map into this fundamental picture where you have the radiation system still, but then now the black hole has been replaced by this thing that's sometimes called the quantum dot, some strongly coupled quantum system. From this point of view, it's clear that the map should act as the identity on the radiation, because R could be any auxiliary system, right? I could have another auxiliary system over here somewhere, or another one over there, and the map shouldn't care about, which one is the one which the black hole is going to evaporate into, because we could change that. I'm going to refer to the left side of this diagram as the effective description, and the right side is the fundamental description. I've been saying that already, but let me formalize it. Okay, and so the general picture we're interested in is finding this holographic map from the effective description on the nice slice, including the black hole interior, into the fundamental description of the black hole microstates coupled to the radiation. So this is a mea culpa here. Sorry, I'm going to treat everything using these tensor product Hilbert spaces. Really, they should be algebras and so on. I don't think that that's a serious issue, but anyways, I'll apologize for it because I should do that. Okay, so any questions so far?
Yeah, hi, Daniel.
Hi.
I don't have a question, I have a comment.
Okay.
You started off your seminar by saying that loop quantum gravity says that space-time is not emergent.
Yeah, what I meant by that was that the metric is a fundamental degree of freedom in loop quantum gravity, whereas in a picture where I would think there's emergent space-time, there wouldn't be a metric in the fundamental description.
Well, I mean, look, I'm the only loop quantum gravity person in the seminar, so I'm the only person who can respond to that.
Okay, sure, go ahead.
And that statement is incorrect.
Okay.
In fact, loop quantum gravity, it has always been understood for the past more than 30 years that space-time is necessarily an emergent entity.
Well, this may come down to what we mean by emergent. So I'm using the definition of emergent to be not having a path integral that looks like a bulk metric in the fundamental, that's a sort of exact formulation of the theory.
Right.
Loop quantum gravity is that you have these holonomies, which are essentially the metric, and you're summing over them.
No, you're just talking about the classical description. When you go to the quantum state space, there is no metric.
Well, then I
would be very happy to discuss this.
I mean, so you can educate me, but I thought you're just supposed to do canonical quantization of these loop metric variables.
Yes, but then you end up with a lot more than what you started with. Yeah, and the
well, I mean, I agree that it's hard to, in loop quantum gravity, it seems hard to recover, the classical metric theory at long distances. But I guess I thought that the idea is that if you sort of tune things in the right way, then the hope is that'll happen.
Well, no, I mean, you do recover.
So could I interrupt, please? I mean, this is an interesting discussion that I'm interested in, but perhaps not related to the subject of Daniel's talk. So
I just wanted to make it clear that I.
Sure, okay.
That's fine. Thank you for the comment. I appreciate it. Yeah, and I'm happy to discuss it more afterwards. Okay. So this is the goal: is to find this holographic map from the nice slice to the fundamental description. Okay, now what's the problem with doing this? Well, the basic problem, as most of you know, is that as the black hole evaporates, we eventually reach a situation where there are more left and right movers in the interior than there are microstate degrees of freedom, right? This happens roughly at the so-called page time. And if the dimensionality of little l and little r is bigger than the dimensionality of capital B, then as we discussed, there can't be an isometry mapping little l tensor little r into B. So if we want to pursue this idea further of the holographic map from the nice slice, then we just have to accept that this map is not going to be an isometry. And in particular, this has the seemingly disastrous implication that there will be a large number of so-called null states in the Hilbert space of effective field theory inside the black hole, which are annihilated by the holographic map. So states which just somehow don't exist in the fundamental description. And, at least naively, that sounds awful, right? Like that sounds like that would be a huge violation of effective field theory that would immediately sort of kill this idea. And in fact, this was, certainly a lot of people worried about this over the years. This is a subset of people who worried about this. So this sounds dangerous, and we're indeed going to need to handle it carefully. But we'll also see that it comes with a big benefit. So this equation is very important. So I want to rest on it for some time. Of course, it's an equation that's not true. So I tried to find a way to notate this. The interesting thing is that this equation is not true. Okay. So if V were an isometry, then if I take a state on little l, little r, and big R, right? So this is a state in the effective description, and I conjugate it by this map, and then I trace out the microstate degrees of freedom. Since V only maps you into the B, the microstate degrees of freedom, okay, if I trace over B, then the V just cancels in the trace. And so I would conclude that the state of the radiation system in the effective description is the same as the state of the radiation in the fundamental description. Okay. And so if that were true, then, for example, that would imply that Hawking was right? That would imply that the entropy of the radiation just sort of increases throughout the evaporation process. It's good for us that this equation is not true, because if V is not an isometry, then I can still try to move it around in the trace, but V dagger V won't be equal to the identity, right? And so then that means that this equation won't be true. And in fact, that's good, because what that essentially means is that information about the interior we'll see can be teleported out into the radiation. And we'll in fact see that this is kind of the basic mechanism behind these quantum extremal surface calculations of the page curve that were done in the last few years. At least that would
Sorry, I have a question.
Yeah, sure.
So is it because of the fact that it's a cross product between V dagger and IR that the V dagger can't be conjugated with the V to B identity?
No. So if you take an isometry and you take a tensor product with the identity, that's still an isometry. So the issue is that V itself, the map from the interior part of the slice to the microstate degrees of freedom, is not an isometry. So I can move the V tensor I around in the trace because the identity doesn't do anything, right?
Okay.
But the V dagger V, I can't get rid of it. Okay. So it's
because it's V dagger, you mean?
Yeah, V dagger V. So if V is an isometry, remember, V dagger V is the identity. But if it's not an isometry, then it could be anything a priori, right?
Okay, so you're saying that V is not an isometry.
Yes, V is, yeah. So that's the proposal, is that V is not an isometry. It's if I want to have this map in this regime where the black hole is old, then V cannot be an isometry. This is just a sort of accounting fact.
Sorry, Daniel, just to understand, I mean, I agree with your conclusion, but just to understand this, so here was the defect, right? What we would call the defect. That's the dimension of the defect.
You mean the B?
Yeah, the mod B. This is just to get, if I'm getting the notation right, it's the dot at the end of the reservoir.
That's correct. That's right. The dot at the end. Yeah.
Right. So and so now what this is saying is that this map can't act as an identity on the radiation after a late enough time.
That's correct. Yeah. Even though it looks like it does, right? It's V tensor I on the radiation, so it looks like it should act trivially on the radiation, but it doesn't.
Right. But why couldn't I have said that, it was that assumption that was breaking down, because you had this B that was coupled to the radiation, and now it's this map is not acting as a radiation. I mean, wasn't that clear from the start that it wouldn't act as the identity of the radiation?
Well, if V were an isometry, it would, right?
Sorry, could you go back to the previous slide? Maybe I'm missing something.
Yeah.
Exactly right. So right, but so here you're saying that L times R has to be mapped into B.
Yeah. But
clearly at late times that can't be the case, even from the boundary theory, right? Because B is
right, but we're gonna see that because V is not an isometry, we are gonna see that the information about L and R gets out into R, and L and little r gets out into big R. We're gonna see that.
Okay, I'm going to agree with your conclusion that V can't be an isometry, but I'm still trying to see how it's derived necessarily from here. Let's say I dropped the assumption that it looked like V times IR.
But I think we can't drop that, because I think it's important that the holographic map shouldn't know in advance which R the black hole is going to be entangled with.
No, it doesn't know in advance. It only knows after the black hole has evaporated, right? Because you had to wait for some time to see the contradiction. So the map doesn't know in advance, but as you wait for some time, it then gets modified depending on the radiation system it was coupled to.
Yes, but I'm trying to, but the thing is so to me, the holographic map is kind of a kinematic thing. So I don't care what the Hamiltonian is, right? I just want to take the state of I give you some state of B tensor R without telling you where I got it. And then I ask you, what's the bulk interpretation, right? Or you can say it in the other way. I give you some bulk state of this entangled with some R, and I want to know what's the fundamental interpretation.
Fine. But why?
And a priori, right? Like this R could be anything. you know, another way of saying it, right? Yeah, I think that's the best argument, but let me just give you another argument, which is that I want if you have a simple operator on R, okay, then I want that operator to coincide in the effective and the fundamental descriptions. You know, if you just measure, you know, a helicity of a photon or something, right? I don't want that to get mapped to some big mess over here. You know, I want it to be measuring the helicity of the photon over here.
Okay. Is that the same as saying that the map has to act as V times the identity? I mean, that's a stronger statement.
Yeah, it's that. Well, that's why I like the other argument more, is because the argument I gave you tells you there should be some constraint, but it's a little bit harder to argue that the map, it has to be that the map has this form. But I think if you say if you want to have it that if I take the black hole and I entangle it with system capital R1, you know, at late times, right? Then the information gets teleported to R1. Whereas if I couple it to R2, then I want the information to go to R2 or R3 or R5 or R15.
Okay.
And so the mechanism I'm describing here will do that automatically, because the way the information gets out has to do with V, which doesn't care about R.
Okay. Okay.
Okay. Anyone else while we're okay. All right. So now let's try to kind of get into what the main proposal and the results are. So the basic idea is this. So we just embrace, we admit, we accept, you know, we celebrate that there is a large set of null states in the Hilbert space of effective field theory inside a black hole, each of which is annihilated by the holographic map to the fundamental degrees of freedom. Okay, sounds bad, but we'll just learn to stop worrying and love it. But to avoid obvious contradictions, we need to somehow say that it's hard for you to tell that that's true if you're living in the bulk, if you're living in the effective description. And so the proposal is that no observer who can only do things of sub-exponential computational complexity can detect that these null states exist. So in particular, the circuit complexity of any one of these null states has to be exponential, because otherwise you could prepare it and then immediately see that it was a null state. Now, it's not obvious that this set of words, yeah, it sounds nice. And, you know, Patrick Hayden and I said some words like this years ago, you know, but okay, you can say the words, but then can you really make this work quantitatively? Okay, and so that the main goal today is to convince you that I can make this work quantitatively. So what I'm going to do is illustrate this idea in a couple models where I'll show that they have the following features. So first of all, I'll show that although V tensor I is not an isometry, it acts like an isometry on all states of sub-exponential computational complexity. Secondly, we'll see that in these sub-exponential states, these states that aren't exponentially hard, and here exponential means exponential in the black hole entropy. In the states that aren't exponentially hard to prepare, you can compute the entropy of the radiation either directly in the fundamental description by using minus trace of rho log rho, you know, which is how you should compute entropy, or you can compute it in the effective description using the quantum extremal surface formula, and you'll get the same results up to exponentially small corrections. So this is some sort of derivation of the QES prescription, at least within these models.
Sorry, Daniel, can I just rephrase the statement you had in bold? That's the statement that there are states that appear distinct in the effective field theory, but that should be identified in the fundamental description, right?
I think it's kind of like that, but I don't, right. I mean, I don't want to say that necessarily, right. So there's an isomorphism between sort of equivalence classes of effective description states and fundamental description states. That's right.
I see. Sorry, let me say it once more. Maybe another way is that if you, let's say you take two states and you compute the inner product in the effective field theory,
Yeah.
you might think it's 0 or close to 0, but in fact, it's larger in the fundamental description.
Yeah, well, yeah, it could be larger or smaller, but I mean, I'm going to argue that for sub-exponential states, the inner product is preserved.
Sure, yeah. And in fact, this larger is when the inner product in the bulk looks like it's gone smaller than e to the minus s by 2. It actually e to the minus s by 2. I mean, is it the same statement or is it a different statement? I'm just trying to understand that.
No, well, yeah. So yeah, I think it's better to say that in terms of the norm, right? So there are. Let me say it another way, okay? So there's two kinds of, in fact, we'll see there's two kinds of bad things can happen, right? There are states which are annihilated, but there are actually also states whose norm is enhanced.
Okay.
And we're somehow saying that those are also sort of invalid, right? I mean, they're sort of in the sense that you sort of can't prepare them. So that's why I'm hesitant to just say it's some cohomology or something, right? There's sort of bad states of both kinds.
I see. Okay. Okay.
So by the effective theory, for instance, if you have Einstein gravity to start with as a fundamental theory, then by the effective, you mean a higher derivative expansion or something?
No, so if Einstein gravity, for me, space-time is emergent. So Einstein gravity will never be the fundamental description. That was the discussion we were having with Deepak.
Okay, I base that, yeah.
So for me, the fundamental description is the dual CFT coupled to a reservoir. If we want it to be really concrete, or if we want to be more fluffy, we can say it's the holographic dual of flat space or something like that.
Okay, even in that case, if you have a fundamental description which is described in terms of a CFT, naturally the effective field theory description will be a derivative expansion in some coefficient, right?
Well, no, I think the derivative expansion is in the effective description, right? So forget about the reservoir. Let's just do it. This is just what we say in ADS CFT, right? So we have n equals 4 super Yang nulls. So that's not a derivative expansion of anything. That's a well-defined conformal field theory.
Precisely, but that's the fundamental theory.
That's the fundamental description. And then we say in effective description, we have 2B supergravity with higher derivative terms that come from string theory and so on.
No. You have an effective description in the conformal field theory as well. I mean, in the boundary theory also you have an effective description, because if you take the path integral and expand the action in the path integral.
No, I think the only effective description in the CFT is the image of the bulk effective description through this map. But in my language, the effective description is always in the gravity description of the problem. So I don't want to say like, low energy hydro.
Have the gravity description too in the effective theory, in the boundary theory. How are you going to say that is the essential effective theory of the boundary theory?
I don't understand what the words effective description of the boundary theory mean. To me, the boundary theory is
So how are you proposing that the effective theory of the boundary theory is the bulk description? How are you proposing that?
I'm saying something fairly precise, I think. I'm saying you take the Hilbert space of bulk effective field theory, and then you have a linear map that pushes it into the Hilbert space of the fundamental description. That's what we can say whatever words we want, but that's what I'm trying to say.
If you have a fundamental boundary theory, how are you going to prove that the effective theory is going to be a bulk description with higher derivative corrections in the curvature tensor or something like that?
Well, you're asking. Well, I haven't told you what the models are yet. The models are going to be more crude than the kind of thing you're talking about. I mean, so why don't we discuss? I think you're asking me how can I derive this picture, I think is what you're asking.
Yeah. How are you going to?
Let's go on and you'll see what I can say about that. I can't answer everything, but I can say some things.
Okay.
Can I just add something to clarify what Daniel was saying?
Sure.
So I believe what you mean, I think the confusion arises because I think what Somdat is saying is that the CFT on the boundary is an effective theory in some sense. But I think the point is that the CFT is an exact quantum mechanical theory, right? It's a fundamental microscopic theory.
Yes.
And the effective theory arises by looking at a suitable sector of that CFT, which correspond to bulk states, which obey the Einstein equation. So
No.
that is the sense in which the gravitational theory in the bulk is an effective theory,
Yeah.
but
Well,
the
yeah,
CFT is not.
Yeah, I agree with that. In some of
type 2b supergravity with the n equals 4 super Yang-Mills theory. Okay, and then you have the fundamental theory to be the Yang-Mills action. Okay, and then the effective theory is got by coupling it to various currents and then taking the Legendre transform of the effective action. Okay, so I mean of the generating function, you get the effective action by taking.
Are you talking about some 1pi effective action or something?
1pi, yeah, 1pi or whatever.
No, but that's some perturbative thing, right? I mean,
No, 1pi is not perturbative, right? Why should 1pi be perturbative?
well,
1pi is not perturbative. 1pi is full.
Non-perturbative is Wilson.
I
think I'm sorry, but the 1pi action is kind of an old-fashioned way to think about quantum field theory. The right thing to think is the Wilson action, and the Wilson action is trivial for a CFT because it doesn't have any RG flow.
No, I mean, are you saying that the effective, but you couple it to various currents, right?
I think that this discussion is not helpful or moving forwards. If so that doesn't mind, maybe this can be discussed in the chat or later.
So why don't we discuss after? Let's see where we get to in the talk, and then we can try again at the end, maybe. So I was saying the things that we can show are true in these models. So we can show that this V acts like an isometry, V times or I acts like an isometry on sub-exponential states. We'll show that we can compute the entropy from the definition and get results that agree with the QES formula. And so they'll agree with this island story and so on. And we'll also see that sub-exponential interior observables can be non-linearly but unambiguously reconstructed in the fundamental description and in a way that agrees with the effective description up to exponentially small corrections or ambiguities. I think ambiguities is probably a better word than corrections. Now, we're also going to be able to address the black hole information problem more directly. So there are various ways of talking about the black hole information problem. Here's the way I like to think about it. So Hawking argued that we can't simultaneously have the following three things. We can't have a finite black hole entropy with a state counting interpretation, a unitary black hole S matrix, and effective field theory valid near / in the black hole wherever there is not a large curvature.
Hi, there's a question about the previous slide. Could we get some definition of complexity of states?
Oh, yeah. Okay, so so we should first talk about the complexity of a unitary transformation. So in the theory of quantum computation, the idea is you want to implement a unitary on a big Hilbert space. And you do that by trying to build it up out of smaller unitaries. So the usual way of thinking about it is you have a finite set, say 3, what are called fundamental gates, which are just unitaries that act on 1 or 2 qubits at a time. And then you can prove that every unitary can be generated by certain sets. They're called universal sets of gates, of finite numbers of gates. But in general, you have to act with exponentially many gates in the logarithm of the Hilbert space dimension. So most unitaries are hard to make, exponentially hard to make in the logarithm of the Hilbert space dimension. The complexity of a state is just the complexity. So it's easiest to say for qubits. So if you start with the all zero state of qubits, and then you want to prepare your state, you ask what's the least complex unitary you have to act with on the all zero state to make the state you're interested in. And so generically, you'll need to use exponentially many gates to make your state. And so those are what I call states of exponential complexity. But there are special states where you only have to act with a sub-exponential number of gates in order to prepare them. So is that clear?
Hi, so when you say sub-exponential complexity, do you mean starting from some simple black hole or starting from vacuum or something?
Yeah, let's say starting from the vacuum. Yeah, I think that's the safest way to say it. So we can include the, preparing the shell that made the black hole or whatever. Yeah.
And exponential and sub-exponential in what? Like it's the number of these fundamental gates compared to e to the minus entropies.
Yeah, yeah. So I want the number of gates that you need to prepare the state, the number of fundamental operations, to not scale like e to the alpha s for some alpha greater than 0, where s is the black hole entropy.
Oh, okay, thanks.
Yeah, this is basically putting a restriction on how complicated of an experiment you can do. So any experiment that we can sort of reasonably imagine, you fall in, you do this, you do that, that's all going to be sub-exponential. Okay. So we were talking about the black hole information problem. And I said that what Hawking argued is that you can't have these 3 things. Now, there are many papers where people show that you only have 2 of these things, and then they say they solve Hawking's problem, but I don't think it's fair. You need to be able to have all 3 of these things in order to say that you're addressing Hawking's problem. So in particular, ADS-CFT showed that 1 and 2 are compatible, right? And so people sometimes say, oh, so ADS-CFT solved the information problem. That was the thing people used to say. But so far, number 3 in ADS-CFT is still a work in progress, as I'm sure you've all heard from Subrat many times. Understanding how exactly you're supposed to think about the interior effective field theory in ADS-CFT remains a puzzling question. And one that I'll say we're going to give a sort of proposal for how it might work here, but I wouldn't say that we'll have worked it out in detail by the end of this talk either. And let me especially emphasize that without 3, you can't distinguish a black hole from a lump of coal. So you really need to have something to say about 3, about the interior degrees of freedom, if you're going to explain the information problem. So what I'm going to do today, or the last thing I'll do today, is I'm going to present a dynamical model which realizes analogs of 1 and 2, and then doesn't quite realize 3 because, as Hawking explained, there's kind of a contradiction, but instead realizes 3 star, where 3 star says effective field theory is valid for sub-exponential observables near or inside the black hole wherever there's not a large curvature. So this is a slight weakening of Hawking's number 3, but one which I think is reasonable. And then we'll see that they're not incompatible, because we see that they're not incompatible because the model has 1, 2, and 3 star. And so at least within this model, I think we can say that the information problem is solved. We can then debate over whether this is the right definition of the information problem and whether the model has enough good features and so on. But at least within the model, this version of the information problem is solved. So that's the end of the introduction. I'm going to go on to talking about the models now. So any more high-level questions first? Okay.
Sorry, Daniel, sorry, just a quick question.
Yeah, sure.
I mean, 3 star is something that's been said earlier, right? But you're saying this is something there's going to be some more specific statement in the context of the model.
Yeah, well, I think the new thing is showing that you can actually, you can say 3 star. I mean, we said it years ago, right? But the challenge is to prove that they're not incompatible, right? Because Hawking says that 1, 2, and 3 are incompatible, and so I want to claim. I don't want to just claim. I want to show you that 1, 2, and 3 star are not incompatible. So I have to give you an example, right?
I see. But in the CFT, I mean, it's clear that 1, 2, and 3 star are not incompatible, right? So what? I mean, why? I'm just trying to understand why.
I don't think it's clear because I don't know how to think about 3 star, because sub-exponential is the bulk, right? So this means bulk observables that are sub-exponential in the interior, right? So I would say we don't know how to think about those clearly. I mean, of course, you have many ideas, I have many ideas, we all have ideas about it, but I don't think that there's a complete story of how to think about the interior degrees of freedom in ADS-CFT.
I see. So sub-exponential, if I give you a map and then I say, between field degrees of freedom and the boundary, and then I just look at sub-exponential polynomials, that would not be good enough. You'll say something stronger than that. I could have done that, right? I could have, yeah.
Yeah, no, I think that's not right. No, I think that, yeah, no, I think in the thermofield double, you can try to do something like that, but I think it'll break down. Let me think of how to say this. The thermofield double doesn't get you into a regime of trouble, right? Like you need to be past the page time in order to be in this situation, right? So I need to have a black hole that's entangled with something else, which is naively more entropic than the black hole, right?
No, it does.
In that setup, I need to talk about the interior degrees of freedom.
No, the thermofield double does, right? You can look at these time shifted states, cousins of the thermofield double, not just the thermofield double, but e to the I HL plus HRT acting on the thermofield double, and then you'd get the same trouble once T becomes large enough.
No, sorry, not if you just consider those states. I mean, maybe if you do superpositions of them and so on, right? But if you just look at those states, then the entropy of the left black hole always equals the entropy of the right black hole. So you can sort of just barely be a.
You'll get too many of them, right? And you have to argue that.
Well, yeah, if you try to reconstruct operators on the big slice at very late times, that's true, right? But I don't know of any proposal. You know, if you evolve up, you know, for here it would have to be a sort of polynomial amount of time, right? And then you try to reconstruct operators on that nice slice. I don't know how to do it, right? In particular, you can't use HKLL because you have to evolve way past the scrambling time to get into the situation where there would be a contradiction. And then when you try to evolve back, you'll run into high energy physics, right? So you can't just evolve back everything out like you do at early times.
Okay, fine, yeah, it's gone, yeah.
Yes, I think it's crucial here that we're in the regime where you're past the scrambling time and you can't just do HKLL. Yeah.
Okay.
And in fact, I won't explain it in the talk, but it won't surprise you to hear that I can prove that that something like HKLL can't possibly work in this situation, essentially because, as you know, the operators have to be nonlinear.
Okay, thanks.
HKLL is always going to be linear. Yeah.
Okay.
Good. So now let's get down to business. So the dynamical model I mentioned here, I'll talk about at the end. I'm first going to start in a static situation where it's easier to understand how things work. So here's the idea. I'm going to give you a proposal for V. I just take some finite dimensional Hilbert space. So if you want, you can think of these as being qubits. I'm not going to use that language, but we easily can. So we have the left moving degrees of freedom, the right moving degrees of freedom, and then some additional states that I just hold fixed. I choose a random unitary transformation in this Hilbert space. And then I split the output of the unitary into two parts. So there's a part that's going to be B, because remember, we're trying to make a map from little l and little r to B, okay? So part of that output is going to be B, but then I also am going to project onto some definite state of some subset of the outgoing degrees of freedom P. And then you'll see in a minute that it's a good idea to multiply by this factor of the square root of the dimensionality of P. Okay, so this is just some map, okay, some candidate map. I'm going to try to prove to you that it has various nice properties. The first thing to notice is that this V is not necessarily going to be an isometry because of this post selection here. So if I didn't put this post selection here, it would be an isometry, but because of the post selection, it's not. Okay. Now I want to emphasize, just because a lot of people are confused about this kind of thing. So I'm only drawing this U once from the ensemble. So, and then the U is fixed. So I'm working in a fixed theory. I'm not doing this thing called fundamental averaging. Okay. It can be confusing because I'm still going to use averaging to learn about the features of a typical U, but for the actual model, I just want to pick a U and stick with it. Okay. So let's just do some basic calculations.
So could you give an example of the sort of thing you have in? Could you give a concrete example?
Example of what? This looks like an example.
Example of whatever black hole you're talking about and whatever left and right sort of degrees of freedom and
I'm telling you the model here. This is a model of a black hole. You know, there's the left and right movers behind the horizon. They get mapped through a random unitary into this B, and I have this post selection. I'm not claiming that it's n equals 4, I'm not claiming that it's whatever 2A string theory compactified on your favorite Calabi-Yau or something, right? It's
That's all right. That's all right. But
yeah, this is
you're just assuming that there's some unitary matrix which takes you from LNR to B. That's all you're assuming.
Yeah, that's all I'm assuming. Yeah, I'm assuming that the U is random, because if we pick some particular U that's simple, what the stuff I'm about to say won't be true, but generically it'll be true.
Okay.
Yeah. So let's think about what some of the generic properties of this V are, right? So
could I just ask a question? What does psi that psi naught sub f? What does that stand for in the Blackwood model?
yeah, so whenever you do this, it's good to hold some of the degrees of freedom fixed so that you don't try to do everything at once. The reason this is here is basically because I don't want to talk about generic black hole microstates. So if we look at let me go back to the picture here, right? So L is kind of keeping track of how you made the black hole, right? The left movers fall in, okay? R are the modes that are going to be entangled with big R according to Hawking, okay? So if I allow this L and this R to vary completely arbitrarily, then I'm considering very sort of general states in the black hole Hilbert space. And those are hard to think about. So for example, I'd like to restrict to states where you make them by just a fast collapse, like you throw in a shell and then you wait for a while and maybe you throw in a few more things, but you don't try to build up a sort of totally generic microstate. We can also talk about that, and that story involves getting rid of this F, but this F is sort of here just to kind of to give us the option to not talk about generic microstates. Does that make sense?
I'm not. Okay. Oh, okay. Yeah, maybe we can talk about this later at the end.
You can say intuitively it's just there so that we can restrict to talking about black holes that we made quickly, something like that.
Okay, I have a confusion that has always confused me. Can you go back to the picture where you have this L and R states going, and the bigger, yeah. So this R states, apparently they also go inside the singularity, right? Because that straight line does represent the singularity.
Yeah, this is the singularity right here. That's right.
So in what sense is R and L different in the sense of their final states? Because
I'm talking about a Cauchy slice that doesn't go near the singularity. So near the singularity, I don't know what happens. I'm not solving that problem here. I'm trying to understand the emergence of the space-time away from the singularity.
Okay.
Because Hawking's paradox doesn't require you to know what happens at the singularity. That's the beauty of it. It's a paradox that has to do with only regions where the curvature is small.
No, you distinguished L and R by saying that L goes to the singularity where R is.
No. What I said was that no, little L and little R both go into the singularity. What distinguishes them is that little L keeps track of how you made the black hole. When you throw things in, they end up in little L. Little R is the thing that in the Hawking's picture is entangled with the radiation.
The radiation is bigger, right?
Yeah, that's big R. So little r and big R will be entangled in Hawking's picture of what's going on.
Yeah, but if little r ultimately goes to the singularity, then
so what? So does little l, right? They both do. That's what happens in a black hole. Once you're inside, you go to the singularity.
So once it goes to the singularity, how does the entanglement? What happens to the entanglement?
I don't know, but I don't have to. I'm not going to answer that question today.
But that's a valid question, right?
Yeah, of course. There are always more questions we can ask. If you fall into the singularity, do you end up in another universe? I don't know. Probably not. But that's strong quantum gravity, so I don't have much definite to say about it.
No, but when you're talking about entanglement with the interior states.
But entanglement is a property of a state, and I'm studying the state on the slice that stays away from the singularity.
Yeah, and when the radiation goes off to infinity, one can presume that the little r goes inside the singularity, right? Because
no, you don't have to say that. The point of this slice is that this slice goes all the way out. So you're studying it on a time slice. There's some radiation which has already come out, and it's entangled with little r. Yeah.
No, true, but the final entanglement.
Somnath, if I may interrupt, could we table the discussion to the end of the talk? And, thank you.
Yeah. Okay. So let's study the model. Okay. So So the basic, so we're going to have two weapons to study this kind of model quantitatively. So the first is there's this so-called Weingarten technology, which I'm not going to explain, but it allows you to compute integrals over the Haar measure on the unitary group of polynomials of the U and U dagger. Okay, so Weingarten is a lattice gauge theorist, and this is a technology that was invented for lattice gauge theory. So people like Spenta will be happy with it if Spenta is still around. Yeah, he is. But here for us, it's just a tool. We're going to use it to study typical things. So for example, we can pick two states, psi1 and psi2, and then we can look at what happens to their inner product when we act with this V tensor I, okay? And on average, so this is some integral involving U dagger U, and we can compute it, and we find that we get just back exactly the inner product of the states in the effective description. So this is the first indication that we preserve the inner product on, at least on, for any particular pair of states, we're likely to preserve the inner product. That's what this says. Now you might say, okay, well, fine, but you were averaging, and we don't really want to be averaging. We want to have a fixed U. So to make sure that this is really true for a fixed U and not just on average, we have to look at the fluctuations, okay? So here
where is the U in the integrand?
It's inside of the V, right? Because V is defined like this.
Yeah, okay, great.
Yeah. So then we can compute the fluctuation. We can compute the absolute value of the difference of the encoded inner product and the effective inner product, right? And by using this technology, you can show that this is upper bounded by something that's of order e to the minus s, okay? Because B is e to the s. The norm of B, this is the dimensionality of B, so that's e to the s. So the fluctuations are exponentially small. So in other words, V tensor IR is very likely to preserve the inner product, even though it's not even approximately an isometry when B is small compared to L and R, since in that case, there would be many null states. So somehow the reason this is not a contradiction is because if we first pick psi1 and psi2 and then pick U, then psi1 and psi2 are very unlikely to be null states. Okay.
Sorry, what would a generic proof of your second statement look like?
Well, what you mean? How do I prove this?
Yeah, the second statement.
Yeah, so this is right. So the easiest way to do this is you first square this thing inside, okay? So you first do it with squaring the thing inside, and then you just get some integral that involves a U and a U dagger, and you can compute that using this Weingarten thing, and then you can use Jensen. So that gives you the bound without the square root. And then you use Jensen's inequality to turn the integral of the square into the integral without the square, and then you have to take the square root here.
I think Stanford has a paper which does this. Anyway,
well, I'm not sure. I mean, this kind of calculation has been done many times over the years. Yeah, I mean, the technique is a standard technique. Here I'm using it to show that the fluctuations of the inner product are small.
No, he had a paper entitled Subleading Weingartens, and I attended that talk, so I know.
Yeah, I know, but he was doing something different. I know about that paper too. I mean, he was using the same technology, but that's if you have a hammer, there are a lot of things you can do with a hammer, right?
Oh,
yeah.
Okay, so I just want to confirm one thing, that when you say V cross IR is very likely to be to preserve the inner product, do you mean that on an average it preserves, but it's not exactly isometric, right? Because fluctuations are there.
Well, yeah. So let's be careful. So it's very likely to preserve the inner product of these two states.
Okay.
So I pick two states, and then I pick U. So when I pick the U, I have to pick the states first and then pick the U for this calculation. Okay. We're going to do it in the other order in a minute, which is what we really care about. But first, let's do it in this order. Okay.
Okay.
Then it's very likely that this preserves the inner product of these two states, essentially because it's very unlikely that these two states are going to be ones where the norm is decrease the lot or increase the lot. Okay.
And what was special about these two states? I may have missed this.
Nothing. You could pick any two. This calculation works for any two states. And I want to emphasize that, I said this already, but let me emphasize that the suppression of the fluctuations is exponential in the black hole entropy. So this works up to order e to the minus s black hole over 2. Okay. So the corrections to this are very small. Now,
I have another question. Like, it seems that what you should really be doing is that if you average over U, you should take the difference between what you get by averaging over U and what you get by not averaging over U. You take the difference of those, right?
yeah, that's what this is doing, right? That's what this is doing. I'm computing the fluctuations. So
No.
if I can show that I showed that this statement is true on average, and I showed that the fluctuations are small, that's the same as showing that it's true for a generic sample.
Why is that?
That's probability theory, right?
Oh.
Like if you know the right, I mean so something just being true on average doesn't mean it's true in a typical sample, because the fluctuations could be large. But if the fluctuations are small, then it means that usually it's true.
Anyway.
Okay. So let me try to give you some intuition for how this happened. Okay. So I'll show you the mechanism using a simpler model. So in this model, I'm going to get rid of the left moving modes. I'll just have the right moving modes in the interior, and then I'll just propose a holographic map where I just, so this is a set of eigenstates of the interior right movers. Okay. And then I just define the encoding of that into capital B to be like this. I just take a uniform superposition over a complete basis of black hole microstates with phases that are chosen randomly. Okay, so they all have the same norm. It's a uniform superposition. I have to put this in to normalize the state. And then I have these randomly chosen phases. Okay. So this is a very sort of the maximally stupid way of trying to fit a bigger Hilbert space into a smaller Hilbert space. Okay. And then we can ask, okay, if I take these encoded basis states of the right movers and I take their inner product, okay, what do I get? Well, I can use this formula. I get 1 over b times this sum over phases. And so then if little n equals little n prime, so they're the same state of the radiation, then the phases cancel and I just get 1. But if I take n and n prime to be different, so they're not the same eigenstates of the right moving modes, then I get something that's exponentially small. And this is true even if the radiation system is much bigger than the black hole system. So in other words, you can fit quite a large number of nearly orthogonal states into a Hilbert space, and in fact, many more than the dimensionality would suggest. There is some limit on the process, so I can't fit it into an exponentially smaller Hilbert space. But for the page curve story, it doesn't have to be exponentially smaller. So I can fit it into a Hilbert space that's quite a lot smaller and still be almost orthogonal. I, of course, can't be exactly orthogonal because of linear algebra, but I can be almost orthogonal.
Yeah, I have a question from the previous slide. So it's, I mean, we have seen that the fluctuation is 0. That means that V is not a isometry. But we know that if we have no post selection, that the fluctuation should be 0, right? Can we see that?
Yeah. So I put, so that's true. So there's an exact formula for this, which I didn't write, which is 0 if there's no post selection. But I turned it into a bound. So this bound is not optimal. I threw out the terms that would have let you see that.
Okay.
Yeah. Okay. So and in fact, this idea has shown up in computer science. There's something called the Johnson-Lindenstrauss theorem. So I just mentioned it here. Okay. So far, what we showed is that the inner product between any particular 2 states is likely to be preserved up to order e to the minus SBH over 2. Okay. So that's nice, of course, but that's not the statement that I made before, right? What I would like to say is that for any particular U, it's very likely that the inner product is preserved up to these small corrections for all states of sub-exponential complexity. Okay, so that's a stronger statement because this requires us to pick the U first and then discuss the states, right? The proof of this uses some machinery, which I will not have time to explain, especially given the speed we're going, which is called measure concentration. So just to give you an example of the kind of result which shows up in the theory of measure concentration, There's this theorem which is due to Max, who is a mathematician, unfortunately recently deceased. This is from some talks she gave at the Institute for Advanced Study, maybe 10 years ago. For any kappa Lipschitz function from the unitary group to the real numbers, there's this incredible fact that if you look at the probability that the difference of the function from its average exceeds some epsilon, this is actually exponentially suppressed in the n of un. So basically in a high dimensional space, the probabilities of deviations from the norm are exponentially suppressed. Okay. There's a lot of fun that goes into understanding why this is true. It's not true in all spaces, but it is true on the unitary group. But I don't have time to go into it. I'll just quote a result for you, the details of this formula. I show you the formula so you can see there's a formula. The details of how I got to this formula, I'm not going to go through, but basically using this theorem, you can show that the probability that if you take the supremum over all sub-exponential states, you look at this question of is the inner product preserved or not, and you want to know the probability that for any particular two sub-exponential states, the norm is not preserved by more than some exponentially small amount, then you get this thing which is suppressed by e to the minus b. So this is actually a double exponential suppression in the black hole entropy. Okay, there's this factor in here that grows, but then there's this factor here that's smaller. And this is true for any alpha greater than 0, so I can pick alpha to be small. All right. So this is just a fancy way of saying the thing that I said. For any particular u, it's very likely that the inner product is preserved up to exponentially small corrections for all states of sub-exponential complexity. All right. So, okay, sorry, that's a bit technical. Ask me later if you want to know more about what goes into showing this. Okay, so now let's do the quantum extremal surface formula. We can introduce what I'll call the Hawking state. So we have some entangled state of the right-going interior modes in the radiation. So this is the Hawking pair entanglement. And then just so that I can have a pure state, I'll purify the left movers, which remember are keeping track of how the black hole is made. I'll purify them onto some reference system, capital L. Okay, that's a standard thing that people do. So yeah, see, L is just a reference system that keeps track of how we made the black hole, and this chi is the Hawking entanglement, this chi out. Okay, so here's some sort of picture, right? So here's our encoding map. We feed in this entangled state of the Hawking entanglement into little r and the radiation capital R, and we feed in some entangled state of the left movers in this reference system L. And so this is the bulk picture of that. We have the Hawking entanglement, and then this L is entangled with some reference system that I didn't draw because you can think of it as being outside of the system. And then our goal is to take this state, here it is, this is just turning it into a density matrix, and then we want to compute the entropy of the radiation system R. Okay, so if we want to, for example, if we want to compute the page curve. So we can use this Weingarten or Haar technology again. So for example, we can compute the second Rényi of R. Okay, so that's the integral of e to the minus S2 of R. This is the same as the trace of psi R squared. And at large B, you just find this result. So it's the sum of e to the minus the entropy in Hawking's picture, plus some term that goes like 1 over the black hole dimensionality times the e to the minus the Rényi entropy of L. Or in other words, the Rényi entropy is the minimum of two options. There's the Hawking result, but then there's this other option, which is basically the entropy of the black hole plus the entropy of the stuff that's inside. And so the same is true if you replace the second Rényi entropy with the nth Rényi entropy, although the calculation is a little fancier. And then if you take n to 1, you get the von Neumann entropy, which is thus given by the same formula. And this is exactly.
Could you go back to the previous slide?
Yeah.
So how do you go from the first statement to the second statement?
Okay, so so I should take the logarithm of this, right, to get the second Rényi entropy. Okay. Technically, I have to show the fluctuations are small, which I did, but I suppressed that here. Okay. And then so whichever of these terms is bigger will determine this, right? So then whichever of these two terms is bigger will be determined by whichever of these is smaller. Okay.
Oh.
So this is just the log of minus the log of whichever term is bigger. That's what this is.
I mean, essentially, it's a sum of those two, but they could be comparable also, right? I mean, in that
Yeah,
case,
yeah. So yeah, if they're comparable, things are more. So usually they're not though, because they're both exponential. So yeah, there's a crossover regime where this formula I wrote here is not correct, and you have to be more careful. I'm staying away from the crossover regime because we're interested in the sort of. We're really interested in the asymptotics, not right at the crossover. You can also compute the crossover, but then there are more terms here I have to write. Actually, not for the second Renyi entropy, but for the higher entropy Renyis, there are more terms I have to write.
and also when you're averaging over U,
Yeah.
What is the S2 of psi r that you? What is the psi r that you get? I mean, in the second state, what is the psi r? Yeah.
This is the psi r for a typical U. Yeah.
For a typical U.
Yeah, for a typical U. It's typically given by this. But you're interrupting the punchline. So let me say the punchline, which is that this is precisely the QES result, right? So this answer here is the answer where you don't include the so-called island, right? Then you just get Hawking's calculation. If you include the island, right, then you get the log B is the area of this new quantum extremal surface, and then this entropy here is the bulk entropy of the stuff inside the black hole. So this is exactly what you get from the island formula. And the radiation, the R entropy doesn't contribute here because this purifies that. And the crossover happens right where you want it to happen from the island calculation. But I want to emphasize here that I have not taken the quantum extremal surface formula as input, and I've also not tried to derive it from Euclidean gravity. We've instead obtained it as output from a microscopic calculation of the entropy.
Okay,
So
I have a question.
One sec. I view this as a more fundamental or principled explanation of this island story than the one which is based on Euclidean gravity.
Sorry, but Daniel, in this, there isn't really yet a space-time, right? This is a statement that there are certain random unitary models that have this property. I mean, we don't have space-time and, Yeah.
No, I know that's right. So as I said, I'm proposing a scenario which then you try to implement in a more realistic theory. I'm going to comment on that at the end of the talk.
Okay, I have a more naive.
I'm trying to tell you the mechanism. I'm trying to give you a mechanism which can be realized in sort of more realistic theories than this one.
Yeah, I have a more naive question. When you average over U, the final answer should be independent of any U, right?
Yeah, that's true.
So how can you say that it is dependent on some U?
No,
but
these are just questions about probability theory, Samdana. When you have a random variable, okay, and the fluctuations are small, then the average is equal to what you would expect in a typical sample from the ensemble up to small corrections. That's how probability theory works.
No, I mean, take gravity, for instance. When you're integrating over the metric, it's independent of the metric finally, right? In the same spirit, I'm saying that this should also be independent of any U.
I agree that, but the statement is that the value of the random variable in a typical instance will be close to its average. So I'm computing the average, but the reason I'm computing the average is because I'm trying to learn about what will happen in a typical instance, okay? And I'm allowed to do that as long as the fluctuations are small. That's so-called self-averaging.
I mean, if you expand about some central U, then it's okay. I mean, as is done in when you expand about some background metric.
So that maybe we can discuss this, later, because this is, as Daniel is saying, these are, standard computations done. I think the statement is just that, for most U, there's some answer, and there might be some U for which the answer might be different.
Yeah, that's right. Okay, so I'll do this quickly because I don't want to go too far over here. But so it's useful to see how this calculation goes also in the phase model that I showed before. So let me just do this quickly. So in the phase model, that's the one where we throw out the left movers and we just have the right movers, and we have these random phases. So then I can pick bases for little r and big R, where the Hawking state just has this simple Schmidt kind of form. And then if I encode this state, I get some state like this. And then if we compute the second Renyi of the radiation in this model, we get this sum over a bunch of phases with these Schmidt coefficients dn dn prime. Okay, and this expression will be dominated by the terms where the phases cancel. And there's two ways for the phases to cancel. They can cancel if little n equals little n prime, or they can cancel if b equals b prime. So when n equals n prime, you get a term like this. When b equals b prime, you get a term like this. These are the same terms we had before from the unitary model. And if you turn it into a statement about the second Renyi entropy, you get exactly this kind of page kind of thing, where you get the minimum of Hawking's Renyi entropy or the logarithm of the black hole entropy. And so the so-called replica wormhole contribution, which is this one, comes not from some Euclidean gravity magic here, but instead it just comes from the b equals b prime terms in this sum. So this is some sort of microscopic explanation of where that term comes from. Okay, so that's just an aside, so I don't want to say too much about it. Let's now talk a bit about reconstruction and measurement theory. So this is the question of, starting in the fundamental description, how can we reconstruct the effective description? So this is a topic that goes back a long way. So the key fact for us is the following. So for any sub-exponential states, psi1 and psi2 in the effective description, and for any gamma, some parameter in this range, we can show, again, using measure concentration, that if you look at the difference of the norm of the difference of these two states in the effective description and the norm of the difference in the fundamental description, it's exponentially small. So in other words, what this says is that although V can be highly non-isometric, it's approximately invertible on the set of sub-exponential states. So in other words, you can't have a situation where two states which are very different in the effective description but are both sub-exponential map to the same state in the fundamental description. So in other words, given a state in the fundamental description, it has at most one interpretation in the effective description. It might have none if it's just a very complex state and there's no sub-exponential state that maps to it, and we'll comment on that briefly at the end. Okay. So that shows that there's a certain uniqueness here. Even though there are these null states that the information is thrown away, you don't throw away information that allows you to distinguish sub-exponential states from each other. And so this is crucial for everything, because if you had different sub-exponential states that map to the same state in the fundamental description, just what would we be doing, right? We wouldn't be doing anything sensible. On the other hand, and I have to emphasize this inverse is not a linear operator, because the set of sub-exponential states does not form a subspace. So I can invert, so V is linear, V tensor I is linear, right? But although I can invert, if I restrict it to sub-exponential states, I get a map which is invertible, but that map is not a linear map, okay? And so we're just gonna have to live with that. The reconstruction is gonna be nonlinear, okay? We're of course not the first people to say that, but this is one clear way of seeing it. Now, using this nonlinear inverse, we can reconstruct the quantum mechanics of an interior observer in the fundamental description. Every sub-exponential measurement in the effective description can be turned into a measurement in the fundamental description, with the latter depending on the state. So that's this nonlinearity, but giving measurement probabilities in post-measurement states which agree with the effective description to exponential accuracy. So this nonlinearity is reminiscent of what Subrat and Kyriakos had discussed before. But I would say that the invertibility I just talked about avoids the ambiguities which at least potentially arise there. So the key difference is that for me, there's a map that's linear going one way, which, so in the proposal of Subrat, who's here so we can see if he agrees, but you kind of build things up sort of in little islands in the Hilbert space here and there, but there's no structure that kind of applies to everything at once. So for us, the map going in the other direction from what Subrat wanted to do has this nice global structure that you can take the whole effective description, you can map it into the fundamental description with a linear map, and that pins down a lot of the ambiguity, because then when you try to go the other way, you have to be compatible with that.
So just to say, I worry a little bit that we are comparing apples to oranges, because a lot of these issues arose because there was some dynamics we were trying to reproduce, right? If we just try to do our map in a qubit system, then it's not clear there would be any ambiguities or anything else. So we could, we could do our map just in a qubit system, try and double the number of qubits or something. So
Yeah.
the ambiguities there arise because we tried to get certain dynamics which you're not trying to do yet, right? So I mean, is it mature to say that whether or not there is a
Well, we're also going to come to a different conclusion than you did about typical states. So I'm not going to say too much about it in this talk, but as far as we can tell, the typical ones have firewalls. Whereas
so
you would say they don't. Yeah.
Well, actually, it's not so much that we would say, it's that if you insist that typical states have smooth interiors, which was kind of then we run into various issues. But if you then we can discuss all of these issues of this Maron-Kulczynski. But if you're willing the fact that typical states have firewalls, and then I don't think there's an ambiguity even in our proposal, right? If you say that there are some,
you have to change the rules, right? Because I mean, the whole thing was based on these equilibrium, having equilibrium states and then showing that constructing a smooth interior.
Right.
So,
right.
so I mean, I agree that the non-linearity. I agree with you that there's the non-linearity, right? I fought it for years, but okay, I don't see a way around it. So this is more about the details of how the non-linearity is implemented, rather than the big idea that there's.
We would have to change the rules in that we would have to give a criteria for which states have firewalls and which don't. But I don't think it's a criteria right now, right?
Yeah. I don't know what that criteria would be, right? I mean, in some sense, I'm kind of trying to use complexity as some kind of criteria like that, right?
Okay.
Yeah.
Okay. Yeah.
But I think the main difference is having this linear map going the other way. That somehow, demanding that we have that, I think gives a lot of extra nice structure.
Yeah. As I said, I understand. So the only question is that in our proposal, the obstructions or lack of obstructions to having some global picture was dependent on some detailed properties. The fact that number of states goes up with the energy, which you don't have here, and also that there's some correlators you expect in typical states which have some function, which are functions of frequency in a particular way. So and what it is that I'm not if one doesn't put those in, then but you can go on in any case.
Well, I will. I'll introduce some dynamics in a minute. So that I mean, it's but they're still going to be crude, like the time will be discrete and so on. But okay, I do what I can do, right? Okay. So this is just one technical slide, mostly just for Subrat. So just expanding a little bit on this nonlinearity. So the type of reconstruction that's most natural in this context is what Akers and Penington called state-specific unitary reconstruction. This is a kind of state dependence. So they're not trying to it's not trying to hide the fact that it's state dependent. It's just this means something very specific. So it has this name for that reason. And so the idea is given a unitary in the interior, a ULR, and a state in this effective description, and then you pick some subset of the fundamental degrees of freedom, like the subset A, it could be the black hole, it could be the radiation, whatever. Then you look for a unitary on the subset that you're interested in, and you want this unitary to act on the encoded state in the same way that you would have gotten by acting with the effective description unitary and then encoding. So sort of unitary then encode is the same as encode then unitary. Okay, so this is a very minimal definition of reconstruction. It's sort of the least thing that you could ask for, which is not totally trivial. And so you can prove the existence of this kind of reconstruction using a decoupling theorem. So that's the strength of this definition, is that although it seems trivial, it's not. So the details of this I don't want to inflict on you, but basically it's saying that if the state on A can't tell, actually this is a typo, I'm sorry. Sorry, this is the state on A bar. So we trace over A. So if the state on the complement of A can't tell whether or not you acted with this unitary, so that's what this is saying. It's just testing whether or not you acted with the unitary and seeing if you can tell. And if you can't tell, meaning that this thing is small compared to epsilon. Oh, sorry, there should be a trace norm here. I'm sorry about that. There should be a 1 here. Then the theorem shows there's a UA such that you can have this up to sort of accuracy square root of epsilon. Okay. So in our model, you can use this Weingarten technology to show that this condition holds with an exponentially small epsilon and A being the black hole if you're sort of before the page time, right? So if the entropy of the radiation is small, in Hawking's picture is small compared to the black hole entropy, whereas if the entropy of the Hawking radiation is big compared to the black hole entropy, so after the page time, then the condition holds with A being the radiation. So in other words, the interior is reconstructed on the microstate degrees of freedom before the page time, and it's reconstructed on the radiation after the page time, which is what you want. That's what Subrat said at the beginning of the talk. There's a small window where neither one works, and you have to use some fancier technology, right? Because these two conditions are not sort of, you know, there's some middle ground between these two conclusions where things are a little more subtle. And then when you do this reconstruction of the measurements, the way it works is for any Hermitian operator, you can have a unitary that implements the measurement. This is just sort of von Neumann's theory of quantum measurement, right? To measure X, you need a unitary that takes the eigenstate and writes the measurement result onto an apparatus. And then you just reconstruct this unitary using what we discussed. So that's the measurement theory I mentioned before. Okay, so sorry, that was a bit technical. Let's go on to the dynamical model. So far, we've only been working on a single time slice, and that's nice, but it doesn't let us address the information problem completely because remember, we had these three things, and one of those things was a unitary S matrix. So we need to introduce some dynamics if we're really going to say that we can include all the features of Hawking's contradiction. I'm sorry this is going over. There's only a few more slides, so I hope you can be done by less than 10 minutes.
Sure, that sounds great. Yeah.
It's okay? Yeah.
No problem. Yeah, no, not at all. No need to apologize. Please go on.
So okay, so let's do dynamics. So as time evolves, the various Hilbert space dimensions all change. So we need to introduce a time-dependent holographic map, which takes L and R as a function of time, and B as a function of, and then maps them into B, which also depends on time, right? Because the slice is getting longer inside. There are more and more interior modes with time, and the black hole is getting smaller, right? So this is getting bigger, this is getting smaller, which is why we eventually run into this non-isometric regime. And so we need to have a rule to come up with this map at each time t. Okay. And then if we're gonna do things that are sensible, we want this map, the time evolution, to be equivariant in the sense that the holographic map at time t+1 is obtained by starting with the holographic map at time t and then just evolving with unitary dynamics in the fundamental description. So in other words, evolve then encode equals encode then evolve. And we would like to have a model which can really include all the ingredients of Hawking's things. So you want to collapse some matter to form a black hole, then watch it evaporate and see if the process is unitary. And at any point in the calculation, you want to be able to understand the emergence of the interior. Right? That's the goal. So we'll start in the fundamental description. So I'll model the collapsing shell as m naught qubits. So here, these red lines here are the initial collapsing shell, whose state we control. And then we'll have some other infalling matter, which we hold in this fixed state psi naught f. So this is just, again, this idea we don't want to consider a totally generic microstate. We want to restrict to black holes that we can form quickly. So we fix these legs, so we just allow these legs to vary. And then the collapse is implemented by some u naught, which we'll treat as random. So that's the first step. That's just collapsing the black hole, watching it ring down. That's LIGO, if you like. Okay. After that, at each time t, we're then going to act with the random unitary ut+1, which does two things. It absorbs an infalling mode, because we could have thrown something in at time t, right? But then it produces two outgoing modes. So that here the outgoing qubits are blue, the ingoing qubits are red. Okay. And then we just keep doing that process over and over. And since at each step we produce two radiation qubits and we absorb one qubit, right? The black hole, which is these black lines, is getting smaller with each time step. So then eventually there's a last U, which kind of spits out just radiation, and then the black hole is gone. Okay, so that's the fundamental description of the dynamics. And if you look at this, it's clearly a unitary S matrix, right? We have just a unitary that takes the ingoing state, including stuff that you threw in later, possibly, and maps it to the outgoing state. All right, so that's condition number 2 of Hawking. condition number 1 is also clearly satisfied, right? It has the black hole entropy is finite because it's just these qubits here. Okay. So that's the fundamental description. All right. This is kind of the dual CFT, if you like, something like that, right? The description that's manifestly unitary and has a finite entropy. Okay, to address the information problem, we also need to understand the interior. And so in this talk, we've said that to understand the interior, what we need to understand is we need to define this holographic map V. Okay, so I have to tell you how to take this picture and turn it into a holographic map V. So here's the idea. So here this is the same picture again, but I just only drew the first couple time steps. Okay, so here's the infalling modes, here's the outgoing modes. The idea is that I do something that at first seems trivial. I take these blue outgoing line modes, the radiation here, and I just bend them around using a post-selection onto a maximally mixed state. And I bend them around using an auxiliary additional maximally mixed state, and then push them back up here. So these are exactly equal. I didn't do anything. I just took the blue lines and I zigzagged them around. Okay, so far it's a trivial thing. But now I'm going to try to reinterpret this picture here as defining my holographic map V. So the idea is I'll take these red lines here, the infalling modes, and I'll call those L at time 2, the left movers, right? I'll take these lines here and I'll interpret those as the Hawking pairs, the right movers, the Hawking interior modes, right? And then here, what I'm saying is that I'll take this line here and I'll interpret that as the Hawking radiation, which I better because it's the Hawking radiation up here. And then you can see that I can reinterpret this as taking the Hawking entanglement together with the infalling state and feeding it into a unitary here, which is some U's, and then post-selecting right here. You see, I'm post-selecting. And so if you look at this picture that way, then it's exactly the kind of map that we were talking about before, except for the U has a little more structure now than it did before, because I build it out of these various U's and there's this bending around and so on. But in particular, the map is still the identity on the radiation, right? This line here just goes straight up there, okay? So all of the non-trivial part of the map is over here on the part that takes little l and little r and maps them to B, okay? So any questions about this? This is a little bit tricky to wrap your head around the first time you see it. Okay, so this is just V. V is just this box here, okay? So then you can easily show that the map is equivariant. I'm showing the pictures, but I won't really bother explaining them. You just you take this definition and you can show that if you take V at time t+1, you can rewrite it this way, and then you can just kind of unbend these and you get VT multiplied by UT+1. So this map respects the unitary boundary fundamental dynamics. And you can also check that the results we had in the static case are going to carry through. So, so it's an approximate isometry on sub-exponential states. You can show that the QES formula is valid for computing the entropy. You can show there's an invertible encoding on sub-exponential states and a reconstructible but nonlinear measurement theory. And actually, you can also show, all of this requires a bit more assumption, or I would say a little bit less rigorous, but you can argue that the Hayden-Preskel scrambling argument that after the page time, if you throw something in, the information comes out quickly. You can show that in this model, but only if you allow the UTs to be a little less random. They can't be hard random, because hard random kind of scrambles too fast. So if you want to derive this log of S in the scrambling time, you need a little more structure. Okay, now just one slide about the final state proposal, and then I'll conclude. So the mechanism here for how information gets out is the same as in the black hole final state proposal of Horowitz and Maldacena. So if you don't know this proposal, you're probably not going to learn it from this slide, but I have to mention this, I have to mention it because it's the same mathematical mechanism, so I have to acknowledge that. So there, the idea is there's some post-selection. You do sort of post-selected quantum mechanics in bulk, and that teleports the information from the left movers out through the Hawking entanglement and into the radiation like this. And so this is the same set of words that we said for how the information gets out in our story. But the interpretation is different. So Horowitz and Maldacena, what they're doing is they're really modifying quantum mechanics in the effective description. They're taking bulk effective field theory. They're saying that's all there is. There's no string theory. There's no holography, whatever. There's just bulk effective field theory, but the rules of quantum mechanics are modified because there's this post-selection of the singularity. Okay. So there are no black hole microstates. There's no holography in their version. For them, they also want to interpret the post-selection as happening at the singularity. Well, for us, there's a post-selection at each time defining VT. And that's important because, well, so their proposal is nonlinear like us, but it's also acausal, whereas ours is perfectly causal. There's no violation of causality for us. You know, somehow I would say we sort of have the good of final state without the bad, or at least without all the bad. We still have the nonlinearity, but that seems unavoidable. Okay, so there are more things I could talk about, but I won't. I'll leave them for the discussion, just mention them here. So you can think about coarse graining in the fundamental description in the simple entropy. There's a beautiful proposal of Engelhardt and Wall for how you're supposed to think about coarse graining in the fundamental description. And you can show that the coarse grained entropy of the fundamental description radiation is indeed given by Hawking's result, which is what you would expect, but it's nice to confirm. There you can have a relation to this Python's lunch story, which I won't try to explain. You can talk about big ADS black holes. So there's a similar dynamical model for big black holes that don't evaporate, which is interesting. You can think about multiple black holes and ER equals EPR, right? How can you have a superposition of a bunch of disconnected states be connected, right? You can see that kind of thing happening. There's some connection to this ghost operators of Kim, Pruskel, and Tang and pseudo-randomness. You can also think more about generic states. You basically do that by getting rid of this psi naught f that I was writing everywhere. But actually, if you get rid of the psi naught f, then a lot of things break. In particular, you can have null states that are not exponentially complex. And I think probably the safest interpretation, although I wouldn't say we proved it, is that probably that means there are firewalls in generic states. They do, however, have this nice feature Lenny pointed out, which is that even if there's a firewall in a generic state, if you perturb the state a little bit and then wait a scrambling time, then that's enough time to sort of restore the horizon for an exponentially long time. And we can sort of see that in the model. Okay, so let's conclude and then I'll be done. So I presented what I and I think our collaborators, we view as a viable scenario for resolving the information problem. Incorporates many of the ingredients which have been previously proposed, you know, post-selection, a cutoff on complexity, non-linearity, quantum error correction, null states, which is a long history, but in particular, Don and Henry, you know, and various other things. It does not use Euclidean gravity, which I view as a major advantage because Euclidean gravity is something that we don't understand at a microscopic level, but it does give results that agree with it where appropriate. So I have to admit, and this is my last slide, that we only realized this scenario so far in fairly crude toy models. So, you know, list of things they don't have, right? Sort of locality, like a definite number of space-time dimensions. I never had to tell you the number of space-time dimensions, right? Don't have continuous time, we only have discrete time. Right? Don't have Lorentz invariance, don't have diff invariance, don't have propagating gravitons, right? A long list of things that the models don't have. The fact that we can resolve the paradox without including these suggests to me that these features are not essential for the paradox, but on the other hand, maybe something I said sort of breaks in some fundamental way once we include these things. So I don't think so, but you know, we should check, right? So, so I'm not declaring victory yet, or it's not completely. I'm optimistic that the encoding map V could be constructed fairly uniquely in ADS-CFT from this extrapolate dictionary, but it would require an assumption that the horizon is smooth for states that you form quickly. I don't see how to avoid assuming that if you just try to construct it by consistency. Ideally, this would be something that we could derive rather than assume, but that would require some non-perturbative version of string theory in the bulk, and I don't know what that is. Okay, that's it. Thank you for listening. Sorry for going over.
And let's thank Daniel for a great talk. Are there any questions? Any more questions, rather?
Yeah,
a couple of questions, which so just to take off on this last slide that you had done. I think think there are two more issues, which two things which should be added to the list. Let me just mention them. You probably already know all of this, but let me just say it for some of the others. One of them is some statistical mechanics properties of the boundary system. So, in particular, as you know, one of the sharpest contradictions about the interior modes arises because you assume first that they satisfy h a tilde is plus a tilde rather than being minus a tilde as it would be for an ordinary mode. And then you demand that, a tilde dagger has the Boltzmann form 1 by 1 minus e to the minus beta omega. And then you demand that a tilde dagger can be computed, as with trace of e to the minus beta h. So those are not detailed properties, but, just those robust properties, and adding in the commutator gives you one contradiction that I think is very interesting, which is hard to see here. The second one, I think, which is interesting is this business that Marolf and Pulczynski emphasized of the Schwarzschild number operator approximately commuting with the boundary Hamiltonian, which is also it's not a very detailed property, but it's some property of the bulk, and that led to, I again think, some of the sharpest contradictions. But those are features I feel should be added. I mean, those are not in this list really, but they're not detailed.
But I think you would agree probably though that once we agree that the interior modes have this nonlinear reconstruction, then at least formally those arguments don't obviously lead to contradictions, right?
Of course, but in some sense we were forced to the nonlinearity because of those arguments. I mean, it would be, if one doesn't have those features put in the first place, then.
But I think here I think you're really forced to it just because of this dimensionality constraint, right? So I mean, in fact we proved the theorem. I didn't quote it here, that just because of this dimension counting facts, the reconstruction is going to have to be nonlinear.
No, fine. Okay. I mean, I agree. You could see that from many different ways, and I see once you have state dependence, then you can get around those issues, but. Somehow those seem to be important issues, right? For instance, this issue of the violation of the Born rule came because of this fact that the Schwarzschild number operator approximately commutes with the Hamiltonian. So it somehow might seem, when you say state dependence, you might want to ask how much state dependence, and they had this argument.
And so we had I didn't talk about, right? So I mean, I intentionally chose the most extreme form of state dependence where you don't even have a subspace, just for each state. You let the operator depend on it. You can, of course, try to, you can indeed have the operator work on a larger subspace as long as it's not too big, right? So in fact, as long as the subspace is a little bit smaller than B, then you can get away with having one operator. But so the reason I didn't present it that way is because it feels kind of arbitrary which subspace you pick, right? I mean, somehow there'll be experiments, whatever subspace you pick, there'll be experiments you're interested in that don't involve that subspace.
No,
it felt better to just kind of go extreme the other way, and
I agree. I'm just worried about these robust features of ADS-CFT not being present.
I mean, I agree about that it would be good to include those. I should also say though that, I mean, the combination of non-linearity plus being willing to tolerate firewalls in generic states gives you a lot of breathing room, right?
That's okay.
Yeah. I mean, it's a little embarrassing, but Subrata, I mean, I had this other paper which I didn't talk about, but with Jaechong last year, about where we studied this commutator of the operator with the boundary Hamiltonian in great detail and many different, and I was hoping that there would be some way of resolving things along those lines, where somehow showing that, it was too naive, this assumption about the commutator and so on. And we tried really hard, and our paper is more than 100 pages long. And in the end, every calculation we did just is consistent with the idea that this energy problem is real.
Okay.
So, I tried my best, but that problem with the lowering the energy and so on, it feels a lot more robust to me now than it did, 5 or 6 years ago.
Okay. Okay. Thanks.
Yeah, sure.
Can I ask a question?
Yeah.
So this left movers and right movers, the small n and small r, they go inside the singularity at the same time, right? Because both are traveling along the light cones, right?
Well, I don't know what that means because we're doing gravity, so time is a.
No, no.
it's a-
I mean,
we can pick whatever time we want.
If you look at the Penrose diagram. If you look at the Penrose diagram, then the left movers and right movers are
No,
going
but
at
I
the
think you have in mind some particular set of time slices, but I mean, I can pick whatever time slices I want.
whatever time slice you pick. I mean, according to the Penrose diagram, they travel along the light rays, right?
Yeah.
Both of them. And
Yeah,
they
except
originate from
masses,
the same line. They originate from the same point.
Yeah.
So what happens is, and the radiation that goes outside, bigger, you measure that at asymptopia, right?
So I measure it as what?
At asymptotic infinity. Once it reaches asymptotic infinity, right?
Well, I don't really, I mean, not really, right? I really measure it at some finite distance, right? I mean, yeah, we can talk about it at asymptotic infinity, but
No, I mean,
I would rather think about it not at asymptotic infinity. I mean, I was thinking about the radiation still as being on a finite location on the Cauchy slice.
in any case, I mean, if you measured the radiation that you measured, the outside radiation,
Yeah.
since the inside radiation almost immediately goes inside the singularity.
No,
So-
I think you're not understanding something about gravity. Let me go back to the picture here. So where is it? Here. So I can adjust this slice out here independently of what I do with this slice here. The only rule is that it has to be an acausal, like it has to be an acausal slice. It has to be a good Cauchy slice. So I can't have points on here that are null separated from a point over there. But other than that, I can do whatever I want. So I can push this time up here, you know, by just kind of wiggling this up here. And if I want to, I can keep this down here the whole time. And I can evolve as far as I want the future of R.
How do you keep that there the whole time? I mean, it's going inside, right? I mean, how do you manage to keep that? It's going inside, going towards the singularity. It's not hovering at the horizon or something. It's going towards the
It's up to me how I draw the slice. In gravity, I can draw any Cauchy slice that I want to, and we can think about the state on that slice. I am choosing to draw a slice, which includes a lot of the early radiation, but does not approach the singularity inside. This is called a nice slice in this language of the black hole information problem, and such slices definitely exist. For example, I think in here we could choose it to be a maximal volume slice. We could attach it here in some way, and then we can extend this out.
No, all I'm saying is L and R, if L goes to the singularity at some time, R also goes to the singularity at the same time, right? Because there's the same distance from the singularity, right? And
I'm not sure. Well, I disagree with this statement, and I will continue to disagree with it. But what are you? So what? What problem do you think follows?
So the thing is that when you measure big R, the small r would have already collapsed into the singularity, right?
No, I don't agree with that. I can draw a slice where I can measure big R, and little l and little r are still away from the singularity on that slice. There is no well-defined global time in gravity. This is just a fact about gravity.
Wait a minute.
Slices you want.
Measuring bigger at the sky plus, right?
Can I ask a question?
Yeah, maybe let's. Yeah, why don't Deepak? I think Deepak has his hand up. I feel like we're going in circles.
Yeah. So I probably missed the portion where you talked about non-linearity, and so I'd just like to understand what that was about. Like, what is this non-linearity, and how does it come about?
Okay,
if it's not too long.
Yeah, well, I can say briefly. So this how should I say this map V is linear. Okay, that maps you from this slice into here. But since it's not an isometry, it's not invertible. Okay. Because there are states to the place. Okay. But the idea is that although it's not invertible as the map from this whole, when its domain is this whole Hilbert space, the claim was that if I restrict to the set of states here, which are sub-exponential, then it's invertible. And that's what I proved somewhere. Let me see. Here. So it looks messy, but this is just proving that it's invertible. So if I have, so that I can't have two different sub-exponential states that map to the same state in the fundamental description.
Okay, so the
So I can invert it. If I restrict it to sub-exponential states, then it's invertible. But the price is that it's not linear, because the inverse is non-linear, because the set of sub-exponential states is not a subspace. So when I restrict to them, I lose the ability to talk about linear operators. It's just some map that I'm inverting.
right. So the non-linearity arises from relaxing the isometric condition.
Okay. The non-linearity arises because, so the map from the effective description to the fundamental description is linear. But if you want to have a map that goes the other way, right, which is how the inverse of the map that I was mostly discussing, then that one has to be non-linear. And and somehow that inverse is the thing we really care about, right? We want to start with the fundamental description and then learn what's going on in the bulk. And so then we kind of have to suffer this non-linearity.
Oh, okay, thanks.
Are there any other questions? Okay, if not, let's thank Daniel for a wonderful talk and also for his patience.
Thanks all. Great to see you again. Hope to see you somewhere soon.
Yeah.
Thanks, Daniel.
Yeah.
Yeah.
Thanks
bye-bye.
again. Thanks. It was
Yeah,
very
bye.
good. Bye.